Hello, Stat 200. Welcome to Lesson 4. This week, we'll be learning about confidence intervals. This is the first inferential procedure that we'll be covering in this course. Inferential procedures use data from a sample to make an inference about the larger population. Confidence intervals use data collected from a sample to estimate a population parameter. A confidence interval is a range of values that are reasonable estimates of the population parameter. In this lesson, we'll be estimating population proportions and population means. Proportions are used with categorical variables, and means are used with quantitative variables. Compared to the first few lessons in the course, our list of topics this week is relatively short. After the review, there are really only 4 main topics to cover. However, they are each a bit more in-depth than what we saw in the lessons that covered descriptive statistics. I'll start with a quick review of inferential statistics. We first saw this definition in Lesson 1. Inferential statistics are procedures that use data from a sample to make a conclusion about the population. If we consider this to be our population, we often don't have the resources to collect data from everyone in the population. So we use sampling methods to draw what is hopefully a random or at least representative sample. We collect data from everyone in our sample, and then we use those sample data to make an inference about the larger population. With confidence intervals, that inference is going to be an estimate of the population parameter. I'll give you an introduction to confidence intervals here. We'll see a few examples of interpreting and applying confidence intervals, and then in the next few sections, I'll show you how to construct a confidence interval yourself. A confidence interval is a range of reasonable values of the population parameter that is computed using data from a sample. The big overarching idea here is that we have data from a sample, and we use those sample data to estimate the population parameter. This week, we'll be estimating population proportions and population means, but in later lessons, we'll estimate the difference in 2 proportions, difference in 2 means, and correlations. Here's a general example. A World Campus academic advisor wants to estimate the proportion of all World Campus students who work full-time. There are more than 14,000 World Campus students, so it would take too long to survey all of them. Instead, what they do is take a random sample of 40 students. They call those 40 students and ask whether or not they are employed full-time. In the sample, 28 out of 40 students are employed full-time for a sample proportion of 0.7 or 70%. They use those sample data to construct this 95% confidence interval. This confidence interval is estimating the population proportion. In this case, they're estimating that between 0.535 and 0.834 of all World Campus students work full-time. Or you could look at this in terms of percentages. Between 53.5% and 83.4% of all World Campus students work full-time. Next, let's look at how confidence intervals are constructed. Here are 2 key points to remember. First, population parameters are fixed values. Going back to the example of predicting the proportion of World Campus students who work full-time, the population proportion is fixed. If we had data from the whole population, we could find that one value. For that particular population, that value is fixed. It does not change as long as the population doesn't change. For the sake of this example, let's say that in the population of all World Campus students, the population proportion is really 0.75. That value is fixed. The second point here is that sample statistics vary between samples. While the population proportion is fixed at 0.75, we wouldn't expect every random sample to have a proportion of exactly 0.75. In the sample from this study, the sample proportion was 0.7. It's relatively close to 0.75, but it's not exactly the same because of what we call random sampling variation. If we would take many samples of n equals 40 from a population with a proportion of p equals 0.75, we would expect most sample proportions to be around 0.75, but they're not all going to be exactly 0.75. That variation is called random sampling variation. If we would repeatedly pull samples of n equals 40 from the population and record the proportion of students working full-time in each sample, those sample proportions would form a sampling distribution. Constructing a sampling distribution is the first step in computing a confidence interval. The confidence interval is a given proportion of the middle of the sampling distribution. For example, a 95% confidence interval, which is the most common, is the middle 95% of the sampling distribution. There are a few different ways to build a sampling distribution. Most of the time, we don't know the population parameter. So in this particular example, the researcher doesn't know that the population proportion is 0.75. All they know is that their sample of 40 has a sample proportion of 0.7. One way to build a sampling distribution using sample data, such as this sample proportion, is with bootstrapping methods, and that's what we're going to cover this week. One of the benefits of the bootstrapping methods that we're going to use this week is that they rely heavily on technology and focus more on conceptual understanding than mathematical calculations. In this lesson and in lesson 5, the technology we'll be using is called StatKey. It's an open access website, which means that it's free, and StatKey will do a lot of different simulations, including bootstrapping, which is what we're doing this week. Before we move on to look at StatKey and bootstrapping methods, I want to talk a little more about interpreting and applying confidence intervals. Confidence intervals are often misinterpreted. Remember that when we're constructing a confidence interval, we're using sample data to estimate a population parameter. We don't know if our sample statistic is less than, greater than, or approximately equal to the population parameter, and we don't know for sure if our confidence interval contains the population parameter. This is an outline, or you could even consider it to be a formula, for a correct interpretation of a confidence interval. I am blank % confident that the blank is between blank and blank, where the first blank represents the confidence level, the second blank is the specific parameter that's being estimated, and the last two blanks are the lower bound and upper bounds of the confidence interval. Let's look at two quick examples. Going back to the scenario from earlier, the 95% confidence interval for the proportion of all world campus students who work full-time was 0.535 to 0.834. To interpret this, I would say that I am 95% confident that the proportion of all world campus students who work full-time is between 0.535 and 0.834. The next example I'll show deals with a mean. Data from a sample of 24-month-old children were used to construct a 99% confidence interval of 33-35 to estimate the mean height in inches in the population of all 24-month-old children. To interpret this, I would say I am 99% confident that the mean height in the population of all 24-month-olds is between 33 inches and 35 inches. Now, let's look at how we can apply confidence intervals to make inferences about the population parameters. A confidence interval contains a range of acceptable estimates of the population parameter. This means that the values in the confidence interval are reasonable estimates for the true population parameter, and values outside the confidence interval are not reasonable estimates for the population parameter. Let's look at two examples. The 95% confidence interval for the proportion of all world campus students who work full-time was 0.535 to 0.834. Is 0.5 a reasonable estimate of the proportion of all World Campus students who work full-time? Any value between 0.535 and 0.834 is a reasonable estimate of the population parameter. Because 0.5 is not within that interval, no, it is not a reasonable estimate. There is evidence that the population proportion is different from 0.5. And one more example. The 95% confidence interval for the mean age in the population of all World Campus students is 29.2 to 34.1. Is 30 a reasonable estimate of the mean age in the population of all World Campus students? Any value between 29.2 and 34.1 is a reasonable estimate. Because 30 is within this confidence interval, yes, 30 is a reasonable estimate for the mean age in the population of all World Campus students. As always, there are some additional examples in the online notes. Now that we have an idea of what confidence intervals are and how they can be interpreted and applied, let's move on to constructing confidence intervals. In order to construct confidence intervals, we first need to construct a sampling distribution. Recall that population parameters are fixed values. There's just one population proportion or one population mean for a given population. Sample statistics vary between samples. Earlier, we saw an example involving the proportion of all World Campus students who work full-time. Even though the population proportion was 0.75, the researchers obtained a sample with a proportion of 0.70. Random sampling variation causes the sample statistics to vary. If we were to repeatedly pull samples of the same size from the same population and record the sample statistic for each random sample, that distribution of sample statistics forms what we call a sampling distribution. For a proportion, this may be called a distribution of sample proportions, or for a mean, it could be called a distribution of sample means. In this lesson, we'll construct these sampling distributions using bootstrapping methods. This process involves taking many resamples with replacement from the available sample. I'll take you to StatKey now to demonstrate this. This is the StatKey website. It's open access, which means that it's free to use. You don't need to set up an account. You should be able to go directly to this site and start using their applications. The bootstrapping options are all here in the center column. In this lesson, we're only going to be working with the first two options. We'll construct bootstrap confidence intervals for a single mean and for a single proportion. I'll start by showing you an example of constructing a bootstrap sampling distribution for a single proportion. StatKey has some data sets built into it. When you first go into bootstrapping for a single proportion, the default is the mixed nuts counts of peanuts dataset. This application was built by the Locks. This is a dataset that they use in their textbook. If you click here, you can see all of the datasets built in for a single proportion. In this course, we'll often use our own datasets. We can enter our own data by clicking Edit Data. For a single proportion, this is where you can enter in the sample values. Count is the number of successes in the sample, and sample size is the total sample size. For this example, I'll use the scenario we saw earlier, where 28 out of 40 World Campus students were working full-time. The count is 28, and the sample size is 40. When I click OK, on the upper right, we can see our original sample data in this table. Again, there were 28 students in the sample of 40 who were working full-time for a sample proportion of 0.700. With bootstrapping, what we're going to do here is repeatedly take random samples of n equals 40 with replacement from this sample that has a proportion of 0.700. Essentially, the probability of success for each randomly selected individual will be 0.700. I'll start by generating one Bootstrap sample. In the first Bootstrap sample, 25 out of 40 were working full-time for a sample proportion of 0.625. This sample proportion is plotted here on this larger dot plot. We'll repeat this process to take a second Bootstrap sample. Again, we're taking a random sample of n equals 40 with replacement from the original sample, so the probability of success for each randomly selected individual was 0.700. In the second Bootstrap sample, 29 out of 40 were working full-time for a sample proportion of 0.725. Now, this sample proportion is added to the larger dot plot here. I'll do one more. This time, 24 out of 40 were working full-time for a sample proportion of 0.600. And this sample proportion is represented by this dot. What we're building on this large dot plot is our Bootstrap sampling distribution. We could keep going one by one, but in order to get a good picture of the Bootstrap sampling distribution, I usually tell students to take at least 5,000 resamples. In StatKey, we can take up to 1,000 resamples at a time, so I'll just click this 5 times. Here, we have our Bootstrap sampling distribution. To recap what we've done here, I've taken a sample where 28 out of 40 students were working full-time, and we randomly took samples of n equals 40 from that original sample with replacement and recorded each of those sample proportions on this dot plot. Later in the lesson, we'll learn 2 different ways to use this sampling distribution to construct a confidence interval. But first, I'll walk through an example of using StatKey to construct a Bootstrap sampling distribution for a mean. When you go into confidence interval for a single mean, the default data set in StatKey is Mustang price, price. Again, there are many data sets built into StatKey, or you have the option to enter your own data. Here, you can copy and paste in your own sample data, or you can upload a file. For this particular example, I'll use the body temp 50 data set. This is built into StatKey. When I select it here, the chart on the upper right now shows us our original sample. These data were collected from a sample of 50 adults. Each dot on this dot plot represents one of those 50 people's body temperatures in degrees Fahrenheit. To construct a Bootstrap sampling distribution for this quantitative variable, what we're going to do is take a random sample of n equals 50 with replacement from this original sample. With replacement means that when we randomly select one person, we then throw them back into the sample before we randomly select the second person. So it is possible that the first and second person in our sample are the same. It's the same idea that we saw when we were working with the categorical variable and estimating a proportion in the last example. Since we are taking a random sample with replacement, some of the observations will appear in our sample more than once, and some may not appear at all. On the bottom right, we have our first Bootstrap sample. The sample size is going to match the sample size from the original sample. This resample was taken with replacement, so we can see that the value of 96.8 appears 3 times in our first Bootstrap sample, but only once in the original sample. We can also see that in the original sample, the value of 100.8 appears once, but never appears in our Bootstrap sample. The mean of the first resample is 98.012. That Bootstrap sample mean is plotted here on the larger dot plot. I'll do this a second time. Again, StatKey took a random sample of n equals 50 from the original sample with replacement. And this sample mean here of 98.008 is plotted here on our larger dot plot. To get a good picture of the sampling distribution, I'll take 5,000 resamples, and here we have our Bootstrap sampling distribution, which in a minute we'll see can be used to construct a confidence interval. Going back to our list of topics, we just constructed Bootstrap sampling distributions. The next 2 points deal with using the percentile method to construct confidence intervals and using the standard error method to construct confidence intervals. The percentile method constructs confidence intervals by finding the middle of the Bootstrap sampling distribution. The most common confidence level is 95%. A 95% confidence interval is the middle 95% of the Bootstrap sampling distribution. One of the nice things about the percentile method is that you can use it with any confidence level. For example, if you wanted a 99% confidence interval, you would find the middle 99% of the sampling distribution. These are the 5 steps for constructing a confidence interval with the percentile method. Some of this should look familiar because steps 1 through 3 are constructing the Bootstrap sampling distribution, which is what I demonstrated in StatKey earlier. From the top, step 1 is to identify the parameter. In this lesson, we'll be working with single proportions and single means. If you have a categorical variable with a dichotomous outcome, in other words, 2 possible outcomes like success and failure, then you're estimating a proportion. If you have a quantitative variable, then you're estimating a mean. Step 2 is to get your sample data into StatKey. There are some built-in data sets, but you always have the option of entering in your own data. Step 3, generate at least 5,000 Bootstrap samples. This will give you the Bootstrap sampling distribution. Recall, when we were in StatKey, this is the large dot plot on the left side of the screen. Step 4 is where we take that Bootstrap sampling distribution and find the confidence interval. Check toTail at the upper left corner of the Bootstrap dot plot, and that will give you the 95% confidence interval by default. If you want the 95% confidence interval, you can stop there. If you want a confidence level other than 95%, you can change the proportion in the middle of the distribution to get the confidence level you want. I'll take you back to StatKey to walk through one example of constructing a confidence interval for a proportion and one example of constructing a confidence interval for a mean. There are several additional examples in the online notes. This is our scenario for the first example. In a sample of 50 World Campus students, 20 are Pennsylvania residents. Construct a 95% confidence interval to estimate the proportion of all World Campus students who are Pennsylvania residents. Whether or not a student is a Pennsylvania resident is a categorical variable with 2 possible outcomes, so we'll be constructing a confidence interval to estimate a single proportion. This data set is not built into StatKey, but I can manually enter it by clicking Edit Data. In our sample, there were 20 Pennsylvania residents out of a total sample size of 50. When I click OK, on the upper right, I can confirm that my original sample data are correct. There were 20 out of 50 for an observed sample proportion of 0.400. Next, I'll build my Bootstrap sampling distribution by taking at least 5,000 Bootstrap samples. This is my Bootstrap sampling distribution. The 95% confidence interval will be the middle 95% of these Bootstrap sample proportions. To find the middle 95% of these dots, I'll check to-tail. The default in StatKey is a 95% confidence interval. The 95% confidence interval here is 0.260 to 0.540. These are the values that separate the middle 95% of this sampling distribution from the outer 5%. To interpret this, I am 95% confident that in the population of all World Campus students between 0.260 and 0.540 are Pennsylvania residents. Or you can convert this to percentages. I am 95% confident that between 26% and 54% of all World Campus students are Pennsylvania residents. Next, I'll walk through an example involving a mean. Construct a 99% confidence interval to estimate the mean body temperature in the population of all adults using the Body Temp 50 dataset in StatKey. This is the dataset we saw earlier. We have data concerning body temperature in degrees Fahrenheit for a sample of 50 adults. In the upper right, under Original Sample, we have a dot plot of these 50 data points. I'll construct our Bootstrap sampling distribution by taking at least 5,000 resamples. This is our Bootstrap sampling distribution. The 99% confidence interval will be the middle 99% of dots on this plot. I'll select to-tail. The default confidence level is 95%, but I can click on the proportion in the middle and change it to 0.99 to get our 99% confidence interval. The values at the bottom here are the points that separate the middle 99% from the outer 1%. To interpret this, I am 99% confident that the mean body temperature in the population of all adults is between 97.974 and 98.552 degrees Fahrenheit. Our last topic to cover in this lesson is the standard error method of constructing confidence intervals. You may have noticed that the Bootstrap sampling distributions we've constructed for both a proportion and a mean have a similar shape. They're both similar to a normal distribution, and this is often the case. Particularly when we're working with larger sample sizes, the Bootstrap sampling distributions will often be approximately normally distributed. When the Bootstrap sampling distribution is approximately normally distributed, we can use the standard error method to construct a confidence interval. This method should only be used when the sampling distribution is approximately normal. If your sampling distribution is not similar to a normal distribution, you should use the percentile method. The standard error method is based on the empirical rule. To review from lesson 2, according to the empirical rule, approximately 95% of observations on a normal distribution will fall within 2 standard deviations of the mean. Applying the empirical rule, if our Bootstrap sampling distribution is approximately normal, then the middle 95% of Bootstrap sample statistics will fall within about 2 standard deviations of the observed sample statistic. The standard deviation of a sampling distribution is known as the standard error. Putting this information together, we get the general form of a 95% confidence interval using the standard error method. The 95% confidence interval will be the sample statistic plus and minus 2 times the standard error. For a proportion, this translates to the sample proportion plus and minus 2 times the standard error, and for a mean, it will be the sample mean plus and minus 2 times the standard error. In both cases, we can get the standard error from StatKey. In the Bootstrap sampling distribution, The standard error can be found here in the upper right corner. Before I walk through some examples, I do want to take some time to talk about the terminology that's used with this approach. We'll see these terms again in future lessons. The point estimate is the observed sample statistic. For example, sample proportion or sample mean. This is also known as the best estimate because if we're estimating a population parameter, the best estimate that we have is the sample statistic. The multiplier is a value determined by the confidence level. This week, we'll only be constructing 95% confidence intervals with the standard error method, so our multiplier will be 2. This is because we know that on a normal distribution, about 95% of observations will fall within 2 standard deviations of the mean. The standard error is the standard deviation of the sampling distribution. And the margin of error is the value added to and subtracted from the point estimate to obtain the confidence interval. If you've watched the news, particularly concerning elections, poll results are often reported as the point estimate and margin of error. For example, you might see 49% with a margin of error of 2%. That means 49% plus and minus 2%, or a confidence interval of 47% to 51%. These are the 5 steps for constructing a confidence interval using the standard error method. Since at this point we only know the multiplier for the 95% confidence level, we can only use this method to construct a 95% confidence interval. Steps 1 through 3 here are identical to the percentile method. This is where we construct our Bootstrap sampling distribution in StatKey. In step 4, confirm that your Bootstrap distribution is approximately normal. If it's not normal, then you need to use the percentile method. If it is normal, then you can use the standard error method. In step 5, use the standard error from the Bootstrap distribution and a sample statistic from the original sample. Plug those values into this formula, sample statistic plus or minus 2 times the standard error, to get the 95% confidence interval. I'll take you back to StatKey again to work through one example with a proportion and one example with a mean. Let's work through this example again, but this time using the standard error method. In a sample of 50 World Campus students, 20 are Pennsylvania residents. Construct a 95% confidence interval to estimate the proportion of all World Campus students who are Pennsylvania residents. We're estimating a proportion. I need to edit data to enter in these observed sample data. There were 20 Pennsylvania residents in a sample of 50. On the upper right, we have our original sample. The proportion here is the one that we'll need to plug into our formula in a minute. I'll go ahead and take 5,000 resamples to build the sampling distribution. This is our sampling distribution. It is approximately normal, so we can use the standard error method. We have the sample statistic from the original sample here, and we need the standard error from the Bootstrap distribution here. I'll plug these values into our formula. 0.4 plus and minus 2 times 0.070. 0.4 plus and minus 0.14 gives us a 95% confidence interval of 0.26 to 0.54. To interpret this, I am 95% confident that in the population of all World Campus students, between 0.26 and 0.54 are Pennsylvania residents. I'll do one more example, this time with a quantitative variable. Let's work with the body temperature data set again. The sample statistic that we need is the sample mean of 98.26. I'll take 5,000 Bootstrap samples to build our Bootstrap sampling distribution. This distribution is approximately normal, so we can use the standard error method to construct our 95% confidence interval. We have the sample statistic from our original sample, and we need the standard error from the Bootstrap distribution here. I'll plug these values into our formula. 98.26 plus and minus 2 times 0.108. 98.26 plus and minus 0.216 gives us a 95% confidence interval of 98.044 to 98.476. To interpret this, I am 95% confident that the mean body temperature in the population of all adults is between 98.044 degrees Fahrenheit and 98.476 degrees Fahrenheit. If you'd like to see some additional examples, there are several in the online notes. This was our first lesson focusing on inferential statistics. We saw how confidence intervals use data from a sample to estimate a population parameter, and we used bootstrapping methods to construct sampling distributions, which can be used to construct confidence intervals. If you have any questions after watching this video and reading through the online notes, please post them to the Lesson 4 discussion board in Canvas.